All right, how's it going, everyone? This is Mr. Yu here, about to go over the second day of Unit 4. Today's objective is to go over determining absolute maxima and minimum, and also about the extreme value theorem. But what we're starting off here is our warm-up from day 1. So remember, in day 1, that was everything about justifying local minimums, local maximums, increasing, decreasing, concavity. So a whole bunch of just fun type of stuff. So for our warm-up for today, we've got 2 questions here and then a third question here on the bottom. Okay. So at this point, you guys should be pausing this video and then trying out the problems on your own. Once you're ready to check, go ahead and unpause, and then we'll go over these problems. Okay, so hopefully you guys got a chance to go over these problems. So for number 1, you're trying to find the locations where f of x has a maximum. So where f of x has a maximum, that if given the graph of f prime, I got my little fun chart drawn out over here. For where we have maximums on f, we would check to see where f prime changes from positive to negative. And where we would have local minimums would be on f, would be where f prime changes from minus to plus. Okay, so we're also confirming that the graph of f of x has horizontal tangent lines at x equals -1, 1, and 3. So we need to be seeing sign changes at those locations too. So at x equals -1, oh, my apologies there. That's actually horizontal tangent lines on f prime, what we're told here. Strictly what we need to find is where does f prime change from plus to minus. So that would occur at x equals 4. Okay, so we're strictly looking for f prime changes signs from plus to minus. Okay, question 2. So this one is a calculator allowed question here. We are given f prime and asked how many relative extremas does f have. So again, the easiest thing to do here is just graph f prime and then check to see how many sign changes there are. So that's why we need our calculator. We're going to go ahead and graph f of x, or f prime of x equals sine of x squared plus 1. And just as a reminder, whenever you are dealing with anything with your calculator, especially with trig, your mode should always be in radians. Okay, so I'm going to confirm that by going to mode, and I'm going to double check, yes, I'm in radian mode right there. Okay, so now go to y equals, I'm going to put in sine x squared plus 1. Look at my graph. Okay, and right now you'll see that like there's all sorts of different x-intercepts here, but since I am only looking at from 2 to 4, how I'm going to be able to just look at that window is by going to window and changing my x-min to 2 and x-max to 4, and then it'll only show me in that location right there. Okay, so how many sign changes do I see? I see 1, 2, 3, 4. So my answer is 4. All right, last one from our warm-up. So let g be a differentiable function such that g is negative for all values, and f prime is given as this expression here. Okay, so which of the following is true? So notice everything in the answer choices have something to do with maximums and minimums on f. So that's telling me I'm going to need to do a sign chart with f prime. All right, so to do that, I'm going to need to set f prime of x equal to 0. Okay, to find the critical points, I'm going to go and factor that. So x plus 2 times x minus 2 times g of x. All right, so my critical points will be at x equals -2 and 2. Okay, so how do I know those are my only critical points and there's none contributed by g of x? Well, because we're told that g of x is negative for all values of x. Okay, so those are going to be my only my only two critical points on this interval. All right, so now I make my sign chart. All right, so if I put in something less than -2, say like -3, then -3 plus 2 is -1. Okay, but keep in mind, all I really care about is not the actual numerical value, but just what the sign is for each factor. So if I put in -3, yes, I know that's -1, but the only part that's important there is knowing that that factor is negative. Okay, so I'd get a negative times a negative times a negative. Again, because g of x is always negative. So that's going to give me a negative interval, less than -2. Okay, so between -2 and 2, say I put in like 0. So 0 plus 2, that's a positive. That's a negative. That's a negative. So that overall will be positive. Numbers bigger than 2, that's going to be positive, positive, negative. So overall, this would be negative. Okay. So what that tells me is that at x equals -2, f of x is going to have a local min. And at x equals 2, f of x will have a local max. All right. Since f prime changes from minus to plus and plus to negative, respectively. Right. So that would be B. Okay. So that ends our warm up. We're now going to go ahead and go over to the notes for today. Okay. So again, today's lesson is on determining absolute maximum and minimum on an interval. Okay. So this statement here is just the technical definition of what it means to be an absolute max or absolute minimum. Okay. I know it looks intimidating at first, but that's all it's saying is if f of c is greater than or equal to f of x for all x in an interval, it just means that f of c is just the biggest value. And if f of c is less than or equal to f of x for all x value in an interval, it's just saying it's the lowest value. It's the absolute minimum of this entire interval. So for these examples down below, we're going to quickly determine which of the following are absolute maximum and minimums, and which of the following are relative maximum or minimums. So we'll quickly do that. So where do I have relative max? Well, that would be 1 here. Okay, at 3, 3. And a relative min would occur at 2, 2. Okay, so again, the reminder of like how should I determine whether or not something is a relative max or a relative min is basically you want to view it as like it's the peak of a roller coaster or the bottom of a roller coaster. Okay, so meaning from both sides, you need to be going down and then back up. Okay, so basically you can't have a relative max or minimum at an endpoint. Yes, I know it goes down here, but there's no other side on to the right of this. So this can't be considered a relative minimum. Okay, but 5, 1 would be my absolute minimum. And 1, 4 would end up being my absolute maximum. Okay, let's do the same for this example. So again, we're looking for relative mins and max, and then absolute mins and max. Okay, so for my relative min, again, I'm looking for the bottom of a roller coaster, right? That would be right there. So 2, 7. My relative max would be here, -2, 39. My absolute min, so where's my lowest point on this interval? That would be right here at -5, -42. And my absolute max where's the very highest of this graph? That would be here, -2, 39. Okay, so what this last example just demonstrated is that relative maximums and minimums can also be absolute maxes or minimums. Okay. All right. But from this activity here, we need to notice like what is the additional thing we need to check in addition to relative maximums and minimums for determining where an absolute max or min could be. Well, notice in this example, we had some of them be on their endpoints of the intervals. Okay. So that's the key thing. That's the key takeaway from all this is not only do you need to check your relative extrema, but you also need to check the endpoints of an interval. Okay. So determine absolute max and minimums. You must also check the endpoints. Okay. So remember, critical points are where you can possibly have those relative max and mins, but then we're also going to check the ends of the interval. Okay. So this leads us into what's called the extreme value theorem. And just like IVT, the extreme value theorem is another existence theorem. So it means that like you can't determine exactly where the extreme value is, but you know there has to be one on an interval. Okay. So what this is saying is so long as you have a function that's continuous on the closed interval, and yes, that is important that it's a closed interval. Then that means that there must be a absolute maximum and absolute minimum on this interval a to b. Okay, so now this definition of the theorem is actually it's not worded like it was up here, but if you do see it worded like with this technical definition, here's what that would look like. Okay, so the actual technical definition, the extreme value theorem would say this. So after f of x, you'd say then there exists a value c on f of x where f of c is less than or equal to f of x for all values x on a to b. Okay, so that would be my technical definition of using the extreme value theorem to show why there must be an absolute minimum on f of x. Okay, so it'd read, if f of x is continuous on the interval a to b, then there exists a value c on f of x where f of c is less than or equal to f of x for all values of x on a to b. Okay, now if I wanted to also make a statement about there existing an absolute maximum, well then of course that would just be changed to say f of c is greater than or equal to f of x. Okay. All right, so let's get into a little bit about why these conditions need to be what they are to prove that there must be existence of an absolute max or min. Okay, so first, why must the function be continuous? Okay, so I think the easiest way to do that to prove why is to show counterexamples. So I'm going to draw an example where f of x is not continuous, and therefore there's no and an example where it doesn't have an absolute max or absolute min. Okay, so here's my first example. All right, so let's say that the interval a to b are here and here, and I'm going to draw, but these are holes. Okay, so there's my graph of f of x. And I have discontinuities at this spot and this spot, which is in the interval a to b. Okay. In this example, we have no absolute maximum, no absolute max or mins. Okay. If we had filled in these holes, then yes, we would have had them. Okay. But because they're open, these points aren't inclusive, we don't have an absolute max or min. We get, like, as we get closer to the holes, though, this value on f of x gets closer and closer to whatever this is, but it never actually quite gets there to being exactly what this is. So for that reason, we don't actually say that we have an absolute max or min. Okay. Like, for example, if this y value was, say, 4, right? We get to a point where we can get to 3.9, 3.999, 3.99999, but we never get to 4. We get as close as we possibly can to 4, but never get there. So for that reason, we say that there's just no absolute max. Okay. So there's one example that shows why you need a continuous function to be able to say that there is an absolute max or min. Okay, here's a second example. All right, so let's say that you have the interval A and B over here, and in the middle, there's a vertical asymptote. Okay, so in this example, you might be going, wait, but isn't infinity and negative infinity your absolute max and mins? Well, no, you can't really say that that is one because an infinite value isn't really a defined value. Okay, so in this case, there is no absolute max or min because infinity and negative infinity are not absolute extrema. Okay, so now the other thing you might be wondering is, well, why does the interval have to be a closed one? I'd mentioned that here, that you must have a closed interval and continuity for there to exist or be guaranteed to exist an absolute max or min. Okay, so once again, I'll draw a counterexample. So let's say your interval A to B are here, and I have continuity everywhere except for the endpoints. Okay, so in this case, f of x is continuous, but only for the open interval A to B. Okay, so in this example, just like we saw here, right, my absolute maximum would be here if this is a defined point, but because it's an open point, again, say that this y value was 4, I get closer and closer to 4, but I never get there. So that means I don't actually have a defined absolute max. Okay, so we're going to go ahead and move on to what are your steps of how you should actually go about finding an absolute max or min. Okay, so how you start off is just like what you would do to find a relative max or min. You first find the critical points. Okay, so remember, finding the critical points means setting your derivative equal to 0. All right, find f prime of x, set f prime equal to 0. But then in addition to doing that, you then also want to check your endpoints. Okay, now because you're going to be doing all this where you're going to be checking y values, there's actually no reason to do a sign chart in this one. Okay, you don't actually have to do a sign chart when you're doing what's called the candidates test. Okay, so all this together is the candidates test. Fitting test for the day of candidates day at the same time. Okay, so what you're going to do is with all your candidates, so that includes your endpoints and your critical points, you're then going to compare the outputs of those values and just pick whichever one's the largest or the lowest. Okay, so let's go through all those steps with example number 1. So we're going to find the absolute max and absolute mins of this function f of x on the interval 1/2 to 4. So your first step is to find the critical values. And you do that by finding f prime of x and setting that equal to 0. So f prime would equal 3x squared minus 6x. You're looking to see when does that equal 0. You then factor this, so 3x times x minus 2 equals 0. And then you find the x values that make this true. So that'd be 0 and 2. Okay. So now I consider, okay, well, my endpoints are 1/2 and 4. And now I have these two critical points, 0 and 2. But I don't really need to test them all because, well, one of these endpoints, or sorry, one of these critical points is not in my interval. 0 is not between 1/2 and 4. Okay. So the only one of these critical points I need to consider is 2. So now what I would do is I would create some way of organizing all my candidates. That could be a table, or you can just write them out line by line. Okay, so I'm going to create a table of the x values I want to test and what their output will be. Okay, so the points I need to test would be 1/2, 2, and 4. So now if I plug in 1/2, that's going to be 1/2 cubed, that's 1/8. 1/2 squared is 1/4, minus, or times -3 is -3/4, plus 1. All right, so 3/4 is the same as 6/8. 1/8 minus 6/8 is -5/8, plus 8/8 will give me 3/8. Okay, now if I plug in 2, I'll get 8 minus 3 times 4, so that's going to be -12, plus 1. So then that would end up being -3. Okay, let's test our last one. So if I plug in 4, I'll get 4 cubed is 64, minus 3 times 16, that's going to be 48, plus 1. So 64 minus 48 is 16, plus 1 is 17. Okay, so now that I've completed my candidate's chart, now I just need to answer the question. So my absolute maximum will occur wherever I have the biggest value, my biggest output, and my absolute minimum would be here at x equals 2 with an output of -3. Okay, so now I just answer the question. F of x has an absolute max at 417, an absolute min at 2, -3. Okay. So the other thing I want to point out on this is that if you're being asked to justify your absolute max or absolute minimum, your candidate's test is the whole justification. Okay. So if you see wording like find the absolute max and min, justify your answer, this right here is sufficient. Okay. So usually I'll see that as being the wording on a free response for finding absolutes and minimums, or they'll just say, show the analysis that leads to your conclusion. Okay, so again, this right here is sufficient. Okay. However, though, on a multiple choice, you got to be careful about the wording. Okay, because on an FRQ, you're always safe in just reporting what the full coordinate point is. Okay, so notice how I wrote 417 is my max. My minimum is 2, -3. But on the multiple choice, they might be asking it in such a way where you need to give the x value for some questions. And then on some other questions, they might be asking you for the y value of your max. So you have to make sure you read your question very carefully to figure out which one they want. Okay, so in general, here's some guidance on that. If you see the word where, right? So like, for example, where does f of x have a local max or min, or absolute max or min? Then that means they are wanting the x values. So the key word there is where. And if they change up the question to say what is the local max or min, value, then they're wanting the y value. Okay, so going back to this question, if I asked you where are the absolute maximums on this function f of x on this interval 1 to 4, you would say the absolute maximum value occurs at x equals 4. But if the question was what is the absolute maximum value on f of x from 1/2 to 4, you would say your absolute maximum value on f of x would be 17. Okay, let's move on to some other examples here. Okay, we're going to do both example 2 and example 3. However, though, I think example 2 would be a good one for you guys to try on your own. So at this moment, I would recommend you guys pause your video, try out the problem, and then play it for reviewing the correct answer. Okay, go ahead and pause it right now. Okay, hopefully you guys got a moment to try out this question on your own. So remember, the first thing you want to do when you're trying to find an absolute max or min is to find your candidates. Okay, find your critical points. That means find f prime of x. That would be derivative of sine is cosine. Derivative of negative cosine would be positive sine. And you're looking to see where that equals 0. So now I need to solve when would this be true? Well, this would be true when sine of x is equal to negative cosine of x, which if I divide over cosine x, I would get tangent of x equals -1. Okay. And by the way, just a quick algebra tip here is whenever you divide both sides, don't divide to completely cancel something out. Okay. If you do that, you're losing answers. But why it's okay here is because I divided and created sine of x and just turned it into a new function. Okay. So sine of x turned into tangent of x when I did that. But if I had an algebra problem where I had like x squared is equal to 4x, you should never divide both sides by x to cancel out an x, right? If you do that, you're going to lose the answer x equals 0. All right, so just a side note. Okay, so now I have to solve when would this be true. So this would be true at x equals, so tangent is negative on the second and fourth quadrant. So that would be 3 pi fourths and 7 pi fourths. Okay, so now that I've found your critical points, now you want to combine these two along with your endpoints, and you want to create your candidates chart. All right, so I need to test x equals 0. I also need to test x equals 3 pi over 4. And well, 7 pi over 4 is not in this interval 0 to pi, so I don't need to test this one. Okay, so plug in 0, you'd get 0 minus 1. Plug in 3 pi fourths, so sine of 3 pi fourths is root 2 over 2. Cosine of 3 pi fourths is negative root 2 over 2. The minus sign there turns that into a plus. So that would end up being 2 root 2 over 2. So that's just be root 2. All right, plug in pi. I'd get sine of pi, which is 0, minus cosine of pi. Cosine of pi is -1. So negative -1 turns that into a positive 1. Okay, so where would I have an absolute max? That would occur where I have the largest y value on this interval, so that would be at 3 pi fourths. And again, on a free response, you're always safe just reporting the entire coordinate point. Okay, so where does f of x have a absolute minimum? That would occur at the point 0, -1. Okay, so before I move on to number 3, though, I do want to go over one additional thing that would be helpful that you might be able to use as a justification on a free response. And this example does a great job of setting this up. Okay. So remember, we're finding the absolute max and minimum values on the interval 0 to pi. Okay. But notice 3 pi fourths is the only critical point on this entire interval from 0 to pi. Okay. So this is actually one where a sign chart actually can help us. Okay. So I'll say it again. If you have a situation where there's only one critical point on an interval, a sign chart can help you with this. All right. So if I create my sign chart from 0 to pi, I have 3 pi fourths here. and I'm doing the sign chart for f prime. Okay, so f prime, remember, was up here. If I put in something like pi halves, which is to the left of 3 pi fourths, well, sine of, or cosine of pi halves is 0. Sine of pi halves is positive 1. So I'd get a positive interval here. Okay, put in something between 3 pi fourths and pi. So this is something that's in the second quadrant. So it's in the second quadrant, and sine values get pretty small the closer I get to pi. So, and cosine values get larger in magnitude and more negative. So something bigger in the negative direction plus something smaller in the positive would make this negative. Okay, so what we've demonstrated here is that at x equals 3 pi fourths, f definitely has a local maximum. But because of the fact that you only have one critical point, there's only one way that you could actually draw this graph. And that would mean that you're only increasing from 0 to 3 pi fourths. And then the graph of f starts to decrease from there to pi. So notice with that type of situation, that relative max also has to be an absolute max. There's no other possibility in this scenario. So if I wanted to, I could have justified this with the sign chart. So what I would say if I did that was f of x has an absolute max at x equals 3 pi fourths, since x equals 3 pi fourths is the only critical point on 0 to pi, and f prime changes from positive to negative. Okay, so that would have been a sufficient way to justify why f of x also has a maximum at 3 pi fourths. Okay, let's move on to example 3. And again, we're going to find the absolute max and minimums of f of x equals the absolute value of 6 minus 4x on the interval negative 3 to 3. Okay, so for this one, I think we have to review really quickly. How do you even take a derivative of an absolute value function? Okay, so this is going to be a useful parent function that you're going to want to know how to take the derivative of. So how do you take the derivative of absolute value of x? Okay, well, I'm going to kind of explain this from a graphical standpoint first. So we all know absolute value of x is shaped as a v. Well, if I draw the slopes of this graph at any point, well, I have a constant negative slope here. I have a constant slope of 1 here. So, and that split occurs at x equals 0. So this is what f prime would look like. And yes, we've seen this graph before. What is this graph? It's the absolute value of x over x. Okay, so that means the derivative of any absolute value function would be the absolute value of itself over itself. Okay, so now for our example here, if I want to take the derivative of this guy, I'm going to have to use chain rule with that. So f prime of x would end up being the absolute value over itself without the absolute value times the derivative of the inside. Okay, now to figure out where the critical points would be, I need to set this equal to 0, or also be considering where's this undefined. Okay, like we can clearly see if I make the top equal to 0, well, then the bottom is also going to be 0, and that's going to make this undefined. So I'm not going to really have a point where this equals 0, but I do have an x value where this would be undefined. And that would be at when 6 minus 4x is equal to 0, which would occur at 3 halves. Okay, so now I need to create my candidates chart. I want to test out my endpoints, -3 and 3. All right, plug them in. So if I plug in -3, I'll get 6 minus -12. So that's 6 plus 12. Absolute value of that is 18. Plug in 3 halves. Well, we already know that that results in 0. Plug in 3, I'll get 6 minus 12. So that will be the absolute value of -6. That equals 6. Okay, so that means f of x has an absolute value, or an absolute max, at -3, 18, and absolute min at 3 halves 0. Oops. Okay, so on the last page of these notes is a full FRQ given in 1987. Yeah, so this is a long time ago, long time ago. And I would say for the most part, like calculators weren't as abundant back then. So this is definitely not a calculator section. All right. Who knows? Maybe this is on the abacus section of the AP exam that year. So yeah, so for this, I would recommend you guys try this on your own and then go ahead and look at the answer key for your solutions. Okay, so I'm going to go ahead and end this video here. And that was our second day lesson. All right, have a good one, guys.